Hello everyone, welcome back. This is Calculus 3. So in this video, we are going to talk about 2.3, the dot product. So in the previous video, we introduced the concept of vectors in three-dimensional space. So in this video, we are going to talk about what does it mean if we are multiplying those two vectors in three-dimensional space. So actually, we're going to call that situation as the dot product. So let's take a look at the dot product definition first. So the dot product, in other words, we also call it as a scalar product. So if you have two vectors, so definitely there are three different components of each vector, and they are in three-dimensional space. So if you are talking about the dot product, what does it mean algebraically and geometrically? So first of all, algebraically, the dot product is the summation, the sum of the product of the corresponding entries of the two sequence of the numbers. For example, we have a U vector, there's U1, U2, U3. U1 is on the x-axis, U2 is on the y-axis, and U3 is on the z-axis. Same thing, there's another vector V, V1, V2, V3 are the components. So what does it mean, the dot product? So algebraically, you're literally multiplying the same component on x-axis, so U1 times V1, and then you are going to adding them, the next components product, U2 times V2, and then U3 times V3. If you're multiplying each entries and then sum of them, we call that as the dot product, okay? So you might be wondering, okay, algebraically, it looks like very simple, but what does it mean geometrically? You want to see more visually the concept of this dot product. So let's say we have a U vector here. I'm gonna just write U vector, and let's say you have a V vector. And then whenever you are going to, look at the dot product, they are going to create an angle between two vector U and V. So geometrically, the dot product is the multiplication, right, of the Euclidean. So what I'm saying is the dot product means you're multiplying the length of U times the length of V. And then at the same time, they're creating the angle. So we are going to multiply all those three components, A magnitude, the vector. You can call it this is A vector, V vector. So dot product visually, it means that you're going to multiply vector A magnitude times the vector B magnitude. And then the angle between U and V, or between vector A and B, that is going to be cosine angle. So you can multiply each magnitude times cosine theta. This is also dot product more geometrical. So we're going to talk about this information in the next slide, but we're going to focus on the algebraically, what that means, the dot product. You're going to multiply each component of each vector. So let's take a look at the example. So I'm going to introduce both case, algebraically and geometrically, in terms of the dot product. So first one, let's find out the dot product, just given the vectors more algebraically. So we know A vector is a given, B vector is a given. Therefore, A times B vector, so actually these are vector, I'm going to make the arrow, means we know 2 times -3, which is a -6. And then you multiply next to entity, 3 times 5, 15, and then -1 times 4, -4. And what did I say? You're going to adding them up. So you're going to adding, right? So I'm going to just make a little bit of space. Adding -4. So basically, -6 plus 15 minus 4, if you calculate it, this is a 5. This is the dot product between those two vectors, okay? So the reason that you're gonna get only one simple number, that's why the dot product also called the scalar, because it looks like just one number, okay? And then one more time, we know that vector can be written by, based on the standard basis, unit vector, ijk. So therefore, you can find out the u vector is simply 2, 9, -1. And v vector is the same as a -3, 1, -4. So therefore, the dot product between u and v, 2 times a -3, -6, 9 times 1, 9, -1 times -4, +4, you're going to adding them. So that you will get number 7. This is the dot product between those two vectors in three-dimensional space. Okay, so algebraically, it's pretty simple. Like dot product means you're multiplying them, and then you're gonna get only one number. So we call also that is a scalar product. Later, we're gonna focus on geometrically, what they mean of dot product, but simply for the first time, algebraic version is gonna be fine. But let's take a look at a couple properties in terms of the dot product. So as you know, algebraically, it's pretty understandable. Since in pre-calculus, calculus 1 and 2, you already observe those property. If you have a two vector, the order does not matter because of multiplication, we don't get the different outcomes. It's going to be same outcomes, although you're changing the order, right? So that's a commutative property. And also you can use a distributive property as well. And then you can multiply scalar first, or you're going to multiply the second vector times the scale. The order does not matter. And then if you multiply same thing twice, it's going to be the magnitude to the second power, because you're multiplying same thing twice, you can find out the magnitude. So these are simple properties of the dot product, just be aware of that. So based on that, let's take a look at example 2. So we are focusing on right now, algebraically, find the dot product. So AB times C, we're gonna multiply AB first because there's a parenthesis. So everything is a vector, which is a given here. So AV vector, if you multiply, it's going to be the dot product. So 1 times 0, 0, plus 2 times 2, 4, -3 times -4, -12. So I got -8. And then you're going to multiply the next vector C, 5, -1, and 3. In this time, we're going to use a distributive property. So -40. And then +8, it's going to be -24. So in this time, when you multiply those two, vector, we got the one number -8, but you are multiplying again this one with the vector. So the answer is going to be the vector with the 3 components, correct? So that's the answer. How about letter B? So A times 2C. So you're going to just do the following, the order. A vector, so which is a 1, 2, 3. And then I'm going to multiply 2 everywhere into the C vector. 10, -2, 6. And then now you're multiplying those are 2 vector according to the dot product system. So that is going to be 1 times 10, 10. 2 times -2, -4. 3 times 8, 6 is 18. So if you're adding them, because it's a dot product, you will get -12. So you have to be careful because in letter A, we already did the dot product and then we got the simple number. Then you're going to multiply with this. This is a scalar. So C vector is going to be, opposite and extended it 8 times. You can think about that way because of the -A. So this is going to be the vector form. B, we already extended a C vector and you're going to multiply with the A vector. It's going to be the same simple number as a -12. Okay, so dot product, it's kind of like a scalar, how much it's going to be how the vector is going to be shrink down or stretch based on this scalar, and this scalar is going to be calculated based on the dot product system. So dot product, to make sure that has the same name, scalar product. Dot product means a scalar product because by doing dot product, you're going to get the simple number. So this has, very important role. You can extend it, whatever the given vector, if you're multiplying it, it could be shrink down, it could be stretched. So therefore, the name is a scalar product as well. Okay, so as you see that, letter C, Okay, this is, multiply same thing twice. So the B, we know that 0 to 4, you multiplying same thing, and then it's a dot product. 0 plus 2 times 2, 4, 16. So the length is going to be 20. So the vector B has a length of 20. So that's also be calculated based on the dot product as well. Okay, so think about the meaning of the dot product. Okay, so it helps us to, find out, a third vector or fourth vector that is stretched from the given vector or shrink down from the, given vector. So that's what the, dot product, or we call scalar product algebraically. And let's really talk about what they mean geometrically, okay? So here is the example. So geometrically, as I mentioned, dot product is a product of the Euclidean magnitude of two vectors and the cosine of the angle between them. So if you have a two vector, so I have a vector right there, and I have a v vector right there. Whenever you have a two vector, multiply them, you will find out the angle between them. So this is going to be the, cosine angle, right? Because, this is a hypotenuse. So if you look at the right triangle here, this is going to be the opposite. The longest side is always a hypotenuse, and the bottom one is going to be adjacent. So according to, we know the information hypotenuse, a vector, and b vector, which is adjacent. So according to SOHCAHTOA, cosine theta is adjacent over hypotenuse, which is adjacent is your kind of like a v vector. And then your hypotenuse is a vector. So therefore, the a and b vector always create the cosine angle. So therefore, you can think about the dot, you can use a dot product, to find out, two vectors of multiplication. Again, you're gonna do the magnitude of the a vector. Okay, so that's the a vector's magnitude. And then v vector's magnitude and times, right, times the cosine theta. That's what they mean a times b product, dot product. Okay, and then we can modify a little bit this product. You can also find out the angle, right? So the most of question in terms of the dot product, the question going to ask you, find out the angle between two vector, right? How would you be able to do that? Because we're going to utilize the concept of the dot product, because this equation is satisfied. Therefore, if you solve for cosine theta, you're going to divide it by cosine theta on both of sides. So this equation is equivalent to a times b dot product divided by each magnitude is going to be the cosine theta. So remember, this is kind of like a mini formula to find out the angle, okay, between two vectors. So the formula is a given, and then let's take a look at the question. Find the angle. Okay, we're going to find out the angle where between the two vector a and b. You see that? So there's an a vector 1, 2, 2. So there's a some vector right there. There's a b vector right there. We don't know exactly where they are, but they are going to be create the angle. They want you to find out that angle, right? So we know that this formula, correct? So one more time, the cosine theta is located between two vectors, right? And it is equal to, we just proved that, equal to the product of the two vectors, right? So if you multiply those two, you are actually multiplying the angle between them to find out the product. So therefore, so a times b is each magnitude times the angle, that's the product. And then if you divide it by, and then if we divide it by a magnitude times b magnitude from this equation. So for example, We know A times B equal to A magnitude times B magnitude cosine theta. I'm going to divide it by A magnitude, B magnitude on both of sides, right? So what happened? We found out A, B cancel. Cosine theta is going to be AB multiplication divided by each magnitude. So we've just found out this equation exactly, right? So we're going to utilize that. We're going to utilize that information. So we have A vector is a 1, 2, 2. It's a given, right? B vector is a given, 3, 4, 0. So cosine theta, we know that A times B divided by each magnitude. So we can find out what the A times the B vector. So this is two vectors of multiplication. So we know 1 times 3 plus 2 times 4 plus 2 times 0. So which is a 3, 8, 0. We got 11. So that's the, dot product, A times B vector. And we can also find out the magnitude A. So the magnitude A is a magnitude formula. Each vector is a square in chapter 2.1, right? So you can find out radical 9, which is a 3. We can find out the magnitude of V. So 3 square, 4 square, 0 square, that is a 25. Okay, we got 5. So we can find out cosine theta is what? A times B product, 11 over 3 times 5, which is 11 over 15. Are you guys following? This is a cosine theta. I want to find out only the theta angle. So we can use the inverse cosine, inverse 11 over 15, right? So you can find out so this is going to be the radian. So if you calculate this one, but I want to convert it to the degree. So if you multiply, do you remember how to find out so degree times pi over 180, you will get the radian. The radian times the opposite 180 over 5, you will get back the degree. So this is the note. So this is going to be the radian already. So you're going to find out the degree, multiply 180 over pi. So if you want to know exactly, go to decimal. Okay. So we found out cosine inverse, cosine -1, and we found out 11 over 15. 11 over 15. So this is going to be the radian, which is an ugly number. I want to convert it to the degree. So you need to multiply. Do you remember? Multiply 180 divided by pi. So you will find out the degree. So the two vectors that is a given, they're going to create 42.8 degree approximately. So I'm going to bring that number. So approximately 42.83 degree. This is the angle between two vector A and B. So you can find out the angle between two vector by using that formula simply. Does it make sense, Gia? So that's the geometrically how you're going to use a dot product to find out the missing angle between two vectors. Okay, so I think it's a pretty understandable topic. Let's practice a couple more. Okay, so let me go down slowly. So here is a couple things. So they keep asking you, hey, please find out the angle between two vector. So A, you can try, right? What is the vector? I'm going to call A vector. So this is the standard base. So 1, 0, 0, 0, 1, 0, 0, 0, 1. So you just read the coefficient of each I, J, K. That's going to be the vector. So A vector is a 1, 1, 1. How about the B vector? 2, -1, -3. Because you remember, 1 times 1, 0, 0, this is I, plus 1 times 0, 1, 0, this is a J, 1, 0, 0, 1. This is a K. So this is going to be any 1, 0, 0. This is a 1, 0. It's the same thing, 0, 1, 0. This is a 0, 0, 1. So they will get 1, 1, 1. So this is the vector of A. So same thing happening with the B vector. So we know what the A and B vector. Let's use the dot product geometrically using that formula. Cosine theta. We just found out A vector times the B vector, and then divided by each magnitude. So you can find out the A times B, the dot product. This is a dot product. So you can find out 1 times 2, 2. 1 times -1, -1. 1 times -3, -3. So you're adding them. That's a dot product, scalar product. So -2, -3, what you're gonna get? 1 minus 3, -2 is the dot product. So I got -2 right there. And then A magnitude, we got 1 square, 1 square, 1 square, radical 3, correct? And then B magnitude, you will get 4, 1, 9. I already squared of them, so 14. So this is radical 3 times the radical 14. So we have a -2 over radical 42, right? So now you want to find out the theta, right? Only theta. So this is a cosine theta. So theta will be cosine inverse -2 radical 42, and then this is a radian. I want to find out the degree, so you're gonna change it to you're gonna multiply 180 over pi, right? So if you multiply 180 over pi, you will find out the degree. So try that example. Try that, by using decimal. You can definitely can find out. Okay. So if you calculate it, it's going to be about, I already calculate for you, about 107.97 degree. That's the angle, between those two vectors. Does it make sense to you? Yay, we good. One more example. So let me change the color, B. So same thing, we know we can quickly do it. So we have a 2 vectors, 2, 5, 6. So cosine theta, we are looking for the angle between 2 vectors. So you're gonna find out A, B, dot product, and then divided by each magnitude. So what happened? A times the B vector, 2 times -2, -4, adding, 5 times -4, -20, adding, 6 times 4, 24. So if you calculate it, what happened? I got 0. So hold up there. We're gonna think about it. That's okay. And then A magnitude, we have 4 plus 25 plus the 36, which is 65. B magnitude, I have a 4, 16, 16. So you should get 36, which is a 6. So this one will be 0 over, because we got everything. So radical 65 times a 6. So what happened? If the denominator is a 0, always the fraction is going to be 0. So what does it mean? We found out cosine theta is a 0. Theta is going to be cosine inverse 0. So if you remember, cosine inverse 0, if you have a pi over 2, theta is going to be pi over 2. If you have a theta is a pi over 2, if you go to the trigonometry table, or you can use a decimal, that's okay. Then you're going to multiply 180 over pi. You will get 90 degree. So these two angles you have, they're literally creating the 90 degree. Those two vector is a perpendicular relationship. Because the theta, we got 90 degree. Does it make sense? So it's a very interesting. Here, the mathematician found out the theorem. If the that product is 0, always those two vector is going to be the perpendicular. We call that is an orthogonal relationship. So that's what I'm going to talk about in the next space. Okay, so here we go. In terms of the angle, you can find out acute angle, which is between 0 to 90. You can find out exactly 90 degree, or you can find out wider than 90 degree. There are different types of angle. So in terms of the vector, what information gonna give you to find out the perpendicular relationship or parallel relationship or no relationship? So I'm gonna talk about it. I'm gonna talk about that information. If two vectors A and B are parallel, that means one of the vector has a scalar. For example, parallel relationship or parallel between two vectors. So think about it. These are parallel line. So a vector, it is going to be, let's say 1, 1, 1, and then the second vector, let's say 2, 2, 2. A vector times 2 is always the B vector. So if two vectors are parallel line, one of the vector has a scalar and the multiplication with the scalar is going to be the same as the other vector. Okay, same because they're parallel line, right? So there's a scalar C exists. Okay, second, exactly this is orthogonal perpendicular relationship. So perpendicular means orthogonal. So if you took linear algebra, there is a concept of orthogonal. That means two vectors are going to create always a 90 degree. And then we just found out that A vector times a B vector is always a 0. Okay, so we just proved that in above. If A times a B vector is 0, that's always 0, always create the 90 perpendicular relationship. Parallel line, one of the vector equal to scalar times another vector. So this is a difference. Scalar exists, it's gonna be parallel line. Perpendicular, A times a B is gonna be 0. And then if you don't see any relationship, like either parallel or perpendicular, whatever the rest of thing is gonna be neither relationship. Okay, so I really emphasize on, okay? I'm gonna prove it one more time. The perpendicular one. So perpendicular is really important. So we know that if two vectors, A vector, B vector, we know that they're gonna create, if you multiply, they're gonna create an angle, correct? So the angle, to find out that angle, we use a cosine theta, A times the B vector divided by A magnitude, B magnitude, correct? And then we just found out if A times B, so this one, if A vector times the B vector is a 0, then the angle between A and B vector always create 90 degree, which is a pi over 2 radian. Therefore, this is a true statement. Okay, the last statement. If A times the B vector is a 0, then what? A vector and B vector is, or they are, perpendicular relationship. Okay, this is we call orthogonal. Okay, so orthogonal is very important. Okay, so check it out, the parallel line and perpendicular relationship between two vectors. Okay, so since we got this concept, let's take a look at couple example. You're gonna prove that whether those two vectors are parallel line or perpendicular relationship. Let's take a look at the next example. So here, we're gonna find out whether the given vectors are orthogonal, parallel, or neither or other. So always you need to check orthogonal. A vector times the V vector is a 0. And then if you want to see parallel line, A vector is going to be B time or scalar times the V vector. Other is going to be neither. So let's take a look at it. Let's find out A vector times the B vector. So 1 times 3, 3. 5 times 1 is 5. Negative 2 times 4, negative 8. What happened? 0. So we just proved that it means A vector and V vector are orthogonal. Simply mathematically rewriting A vector perpendicular V vector. That's the symbol. Okay, we got it. How about letter B? So let's check A times B. 2 times negative 4, negative 8 plus negative 1 times 2, negative 2. 3 times 6, negative 8. So we got negative 28. This is not equal to 0. So let's look at the pattern. If you multiply 2 times A vector, what happened? 2 times 2, negative 1, 3. We got exactly, actually, if you multiply negative 2, right? Negative 4, positive 2, negative 6. So this is exactly C times A vector. We got B. This is a parallel line. How parallel line? One vector is going to be that side, another vector opposite side and longer because you multiply negative 2. So they're a parallel relationship. Okay, so parallel, one is orthogonal, perpendicular. Okay, so you can see the relationship by looking at the scalar. All right, last one, A times B. So 1 times 2, 2 plus 0 minus 6. Well, this is negative 4, not 0. So this is not perpendicular orthogonal, but also what happened? I don't see anything. If I multiply 2, it's not going to be equal. So this is a neither relationship. So they're going to be maybe create an acute angle or a view like a wider angle than greater than 90. Again, one more time. This is 90. 0 means always they're going to create a 90 degree. Okay. Parallel line, they don't like exactly create the angle, but it's going to be parallel line. They're just keep going and forever together. Then neither it's going to be smaller than 90 or wider than 90 degree. Okay, so that's the neither relationship. So here I show you 3 different, cases when you find out the angle of the 2 vectors. So think about it. So I'm not giving you like too much information. We start from what does it mean of the dot product. We just practice how to calculate it algebraically. And we talk about what they mean geometrically. So 2 vectors create an angle. And then the angle could be 0 or a parallel line or nothing. So think about the meaning and, especially the orthogonal A times B dot product equal to 0, they are going to create the 90 degree all the time. So one more, practice here. All right, so here the vector is a given, but there's a missing information X, but they say they're going to be the orthogonal. So A vector and B vector, they're going to be orthogonal, which means perpendicular. So if it's orthogonal, what happened? A times B must be equal to 0. So we can solve for X. So if 2 vectors are orthogonal, then A times B vector is a 0. So A times B, X times 1 is X plus X times X second, and then plus negative 1 times 6, negative 6. They must be equal to 0 to become orthogonal. So we know X second plus I change that order. And then you can solve for X by, factoring out 3 and 2, positive and negative. So X is a negative 3 when X equal to 2. So whenever X is a negative 3 or 2, the A vector and B vector will be orthogonal, creating 90 degrees. So that's the answer for X, possible X's we just got. All right, so that's it pretty much. We talk about the dot product definition algebraically and geometrically so far. Are you guys happy? Are you, So far, so good. I'm hopefully, I'm hoping you guys are smiling so far. You got this concept, okay? I'm trying to show you guys all the work as much as I can. So another concept in 2.3, let's talk about vector projection. So this is a little bit of application where you're gonna see the dot product. So let's take a look at the question or formula that is given as well. So in calculus 3, you will see a lot of theorem, but you don't need to really worry about the proof stuff. So let's look at where this formula just came from and how to use it. Okay. So just a little bit of wording problem. And I just want to tell you something. So what does it mean, the vector projection? So the vector projection means you have a two vector, u and v, and then let's say u vector looks like this direction, and v vector is going to be looks like that direction. And let's imagine the real life situation. You have a sunshine right there. Okay, and then you have a big tree here. And then because of the tree, you will find out the shadow, which is here. This is not really, covering the entire u vector. U vector is longer. I'm only looking for this length of which is a shadow of the tree. Does it make sense? So to find out this length, we're gonna use a little bit of the, dot product concept. So how to read this one? We call this vector, we call project of u onto, of a v onto u. So this is the u vector. So this v vector, you see that this v vector project onto u. Does it make sense? This means this length of the shadow, let's say this is shadow of tree, and then this is not covering, this is not equal to the entire u vector. So we read this one, the vector projection of, so v vector is a, kind of like a mirroring, onto the sunshine, and then the shadow is going to be created here. So the vector projection of v onto where? U vector. So that's how you read it, the shadow of the tree. But anyway, let's keep talking about it. So we're gonna think about a couple things. So the project, we're gonna talk about a little bit of the formula thing, but you don't need to really worry about it. So we know that the project, so I'm looking for the length of a project, right? U. So we project the projection of v onto u. So we're gonna write it this way. This is what they mean, right? So we're gonna write it project, projection of v onto u. So that's how you write it. So I'm looking for simply shadow of the tree. So this is going to be, what do you guys think? Do you see the right triangle here now? Yes. So here we have SOHCAHTOA. So this is the hypotenuse anyway. This is the opposite, and this is gonna be the adjacent. So simply you're solving for adjacent. So what happened? We can use cosine theta. So cosine theta, because these are given. So this u vector project is a given. So this is the combination between hypotenuse and adjacent. Hypotenuse and adjacent gonna create the cosine, because the cosine theta is what? Adjacent over hypotenuse. Are you following? So what happened? So you found out this information. So let me write it. Cosine theta is adjacent over hypotenuse. So adjacent, we know that this is project u v, which means the projection of v onto u, over hypotenuse. Exactly, this is v vector. So let me minimize a little bit. I don't want to make it too confused, right? So what happened? I'm going to bring this equation here. Cosine theta, we found out Jason over hypotenuse. So Jason is project of, V onto U over hypotenuse is a V vector, correct? So now I can cross multiplication, which means between these two. So cosine theta project UV over V vector. So what happened here? Cross multiplication, project UV equal to V vector times cosine theta. So projection of V onto U, you can find out V vector times cosine theta. Okay, so this is the one thing we just discovered. So I'm going to go down the next slide. So I'm just giving you the idea, right? So projection of V onto U is this red line, shadow of the tree. That's how you read it, the vector projection of V onto U. How would you be able to find out this length, correct? Okay, so we found out this information from the right triangle's characteristic SOHCAHTOA. So cosine theta is adjacent over hypotenuse, adjacent is a project UV, and then the hypotenuse is a U vector. So we kind of like found out project UV equal to V vector times the cosine theta. So this is something we're going to begin. Now, highlighted this part, cosine theta. What happened? We already know. We know cosine theta, you can use the formula. We just talked about the angle between two vectors right there. Actually here, all the way up here. Cosine theta is AV dot product divided by each magnitude. So we're gonna use that one. So cosine theta, since we know cosine theta is two vector, in this time U and V, multiply each magnitude. So let me plugging in here. We're gonna plugging in this one into the cosine. So therefore, project UV equal to V vector times what happened? U vector, V vector over U magnitude, V magnitude. So now what happened? The V vector. So actually, this is the hypotenuse, the length. I can put the magnitude. So that's the V. So I forgot the magnitude sign here. So magnitude, because the hypotenuse, that's a length. So we can cancel this. So what we got, project onto V, project of U, V onto U, that's this meaning, is going to be each vector divided by U vector. Are you okay with that? This is the magnitude. This is the length of the project. So this is the project V. So I'm going to put all the length. So think about it. You don't need to memorize this proof. I'm just showing you. I'm going to show you the final formula later, but I'm just showing you where this formula came from. Okay. So we are looking for the length of this amount. So this is a project U V, in other words, the vector projection of V onto U. So we want to know what is the length of the project, this. So that a little bit of background, so SOHCAHTOA, So project, I forgot the length everywhere, sorry about that. This one is the V times, magnitude V times, right, hypotenuse times cosine theta. And then cosine theta is already this formula, so I'm plugging in. So we found out like this formula. If you want to find out the length of the shadow of the tree, you're going to multiply two vector and divide it by what? The magnitude of the U vector. Okay, so now I don't want to find out the length of the project. So we call also this is component UV. So same name. So if you want to find out the length of this vector project, this is the length of the vector. We also call component of V onto U. So we just proved that this is true. We just found out this is proof. The length of the project V. So this is the length of project UV. Same meaning component UV. Okay. And then I don't want to find out the lengths. I just want to find out the vector project UV. Okay. So that's a little bit different formula. So this is, I'm going to write it here. So we just proved that this formula, but now I want to find out project UV without the length. This is not the length. I just want to find out the vector projection. This is vector projection of V onto U. So in this time, we found out project UV. We already know this is going to be the U times V over U. But if you multiply with the unit vector, do you remember the unit vector? U over magnitude. This is a unit vector. So multiply unit vector, you can find out the just vector projection of U onto U, which is not the length. This is not the length. Okay. So therefore, the formula is going to be you have U times V dot product divided by magnitude second power times U. So this is the project vector projection, and the above one is a length of the projection, length of a vector projection. So a little bit confused, I know. So I show you two formula. One is a length, another one is just a vector projection. So highlight it. Projection, the length of the project vector projection, we're going to use this formula, which is we call component vector as well. But if you want to find out the vector projection itself without the length, that is the formula. So we have a two formula that is given that twice in the textbook. Number one, number two. This is not length. This is just vector projection. Now the second one is a length of vector projection, which is that symbol. So think about it. A little bit of, work, but you can simply gonna use that formula that is given. Okay, so I will show you the example step by step. Are you guys okay with that? All right, so let's take a look at the example. Okay, so depending on the question, you need to read very carefully whether they're looking for just the vector projection or the length of a vector projection. So then using the different formula. Okay, so that's how the formula came from. Okay, all right, so here is the example. You see that? Example 7. Find the projection U onto U. So we already found out, which is this formula. This is the project. They're now looking for the length. So project, V of V onto U. So we are writing this is, we just proved that U times V dot product divided by the magnitude of the U vector square and then times the U vector. So this is the formula we just proved it. So find out everything. We're gonna do, this is project U onto U of V. So that is going to be multiply UV. So you multiply those two, -3 plus 20 plus 3. And then you have a square, right? So if you remember the magnitude of the second power, so you have U vector, -1 square, 4 square, 3 square, and you have a second power, correct? So simply the radical and second power, they're going to be canceled. Am I correct? So the inside is going to be just -1 to the second, 4 to the second, plus 3 to the second. Am I correct? So that would be, and then you're going to multiply U vector, -1, 4, 3 here. So therefore, if you're adding them up, 20, actually 20, yep, over the bottom, 1 plus 16 plus 9, 26. And then you multiply the u vector. So the answer, negative, I'm going to simplify 10 over 12, actually 13, negative 1, 4, 3. So the answer, negative 10 over 13, 40 over 13, 30 over 13. So this is the projection vector, the vector projection of V onto U. Does it make sense? So very, very not complicated if you know the formula, but I just highlighted here. Okay, that's it. One more practice, one more time, practice. So we are looking for project of V onto U. So you're gonna find out each vector. So I'm gonna write it. So this is going to be 3, negative 2 vector. This is a 3, negative 2 vector. This is a 1 and 6 vector. So multiplication U and V. So 3 times 1, 3. Negative 2 times 6, negative 12. And then you have the bottom magnitude of, the U vector. So 1 square plus 6 square, and then second power. Then you have a 1 and 6. So negative 9 over 1 times 36, 37. And then they're cancel. So 37, 1 and 6. So therefore, negative 9 over 37, negative 54 over 37. You can go back. Negative 9 over 37i minus 54 over 37j. That's the vector projection of V onto U. That's it. Okay. So you can find out, the vector projection itself, and then the length is going to be much simpler, formula. We just proved that. So if you need to read the question, if they're looking for the length of the vector projection, use this one. If they're just looking for the vector projection, you're going to use the formula. So there are 2 formula is a given. Okay. And then this is the proof where it came from. So anyway, we practiced algebraically how to find out the vector projection. I'm going to do the applicational problem. Actually, this is more important. So let's take a look at this example. Okay. Scale-up projection of velocity. So let's read the question slowly. So in this question, you're going to use all the formula we just discovered here. So what is going on? Let's take a look at it. A container ship leaves port traveling 15 degrees north of east. Its engine generates a speed of 20 knots along that path. See the figure. In addition, the ocean current moves the ship northeast at a speed of 2 knots. Considering both the engines and the current, how fast is the ship moving in the direction 15th north of east? Round the answer to 2 decimal places. So when you read the question, you need to feel it. Oh, there are 2 vectors going on. So I'm going to define the 2 vectors because there is, the velocity vector generated by the engine. There's another velocity vector of the current move. So they are going to be your 2 vector. So let V be the velocity vector because they're talking about the speed generated by the engine. Right? So that's the V vector, which is here. And then they exactly talking about the magnitude. Speed is going to be the magnitude of the V is going to be 20. And they're creating the 15 degree from north of east. So actually in the image, this is the V vector. So this is the 15 and the speed is a 20, the magnitude is a 20. So I call this as a V vector, generated by the engine. Another vector, let W vector be the velocity vector, another velocity vector speed of where? Of the current move, of the current move, of the current move, the ship, current move of the ship. And then what happened? The speed is a 2. Very slowly they're moving. So this is the second vector. And then they have a 40-degree creating right there. Okay, so that's a given. There are 2 vectors given. And then you can fill it. What is the angle between 2 vectors? So by looking at this, the angle between 2 vectors, simply you can calculate it. 45 minus 50, 30 degree. They're going to create 30 degree right there. You can see visually. So what they're asking, they're looking for, considering both the engine and the current, how fast is the ship moving the current in the direction 15 north of the 5th? So actually they're looking for this one, okay? There are 2 vectors, and then they're looking for the component, the vector projection of what? W onto V vector. So let me write there. So in this question, we're looking for, the vector projection of, right, W onto V vector. So they're looking for like this amount, right? This amount, the red one here. So this is the vector projection of W. So W is a keep going, but I want to find out the, how fast onto V. So this is what they're looking for. So this is a vector projection of W onto V. So we need to find out simply vector projection. So this is the length, okay, we are looking for. So this is a little bit tricky question, considering both the engine and current. How fast is the ship moving into? So how fast ship is moving here, right? How fast is the ship moving in this direction? So they're looking for the vector projection of W onto V. Does it make sense? So we are looking for the length of the project, okay, onto V. The formula will be up, this one. So we're gonna go there. V times W dot product divided by the W on, the vector that is, reflect, that is a W vector. So that's, you can set it up, right? And then we know pretty much all the information. So do we know what the product, that product vector? So this part, we know from the beginning, V times the W vector, dot product, each vector's magnitude times each 2 vectors and cosine theta. So therefore, this is given 20 and 2. And then cosine, the between 2 angle, is a 30. So we have 40 times cosine 30. That is going to be 3 radical 3 over 2. So we have 20 radical 3. That's the dot product between 2 angle, and then therefore 20 radical 3 divided by the magnitude is given 2. So we have W. Actually, let me just double check. What is a W? Actually, I made a little bit of we have to divide it by the V. If you go up, sorry about that. So we have to divide it by the U, which is in our case, this is not W, this is a V. So you have to divide it by V. Am I correct? So many people like me, you can make a, so you have to divide it by this one, onto U. So onto, we are onto, V. So that's why you divide it by magnitude of V. So in this time, it's going to be 20. So this is your length. Am I correct? As a decimal, about 1.73. So what does it mean? What does it mean? We just found out this length. Ship is moving slowly. Engine moving, maybe faster. So if they're, generating, together, I want to know, like, if they're moving this amount, how much they're reflect onto V, right? So that's 1.73. So, since we already know, since the ship is moving, the ship is moving, we already know that it is already 20. So this is the 20. This is a 20. So we are actually 20 knots. And then they're adding 1.73 knots. We just calculated. So their total 21.73 knots they're moving in the direction of 15. Northeast. North of east. So that's the final answer. So you can stop here. That's okay. We just found out that length, 1.73 knots. But in this context, they're moving to the 15-degree direction. How much total? It's going to be total 20 plus 1.73. So it's going to be 21.73 knots. Okay. So this is one of the applicational problem. So you can think about it. Okay. So in this question, we, use the project, vector projection formula and plus dot product formula so that you can think about it. Okay, so that was one example. I'm going to quickly go to the next example, the work. Okay, so you can also use a dot product concept when you're calculating the work in a physics, concept. So, we now understand the dot product, what they mean, and we can see how to apply them to real life situations. The most common application of the dot product of two vectors in the calculation of work. Okay, so from physics, if you remember, we know that work is done when an object is moved by force. One more time, the definition of the work. Work is done, right, when an object is moved by a force. So that's what the definition of the work. So when the force is a constant and applied in the same direction the object moves, then we define the work done as a product of the force and the distance the object travels. So basically in the physics you might heard about, work is going to be force times the distance. The force, how much you're pushing or pull, the length, distance, the total is going to be the work. So that's a formula. So in the vector system, force can be, the magnitude of the force, and then the distance is another vector. So you have two vectors, right? Force and distance, because they are two vector, and then they're going to create a cosine. So if you want to find out the work, you can use force magnitude times the distance times the cosine theta. That means force times the distance. So this is in the vector system definition. So same thing we talk about if you have a two vector, u and v, we talk about, the angle between their creating. So to find out the two product multiplication, u vector magnitude, v vector times the cosine theta, same thing apply here. Work is going to be done by force times distance, and those are two vectors. Each force and distance is a vector. So magnitude of force, magnitude of distance, cosine theta, that's going to be the work. So the formula is pretty simple. If you don't have the angle, if the two vectors are simply given, you can just calculate the work. But if you have an angle that is given, you're going to use the cosine theta formula. So let me show you the example. So here we go. Force vector given. And then there are looking for the lengths between P and Q. That's going to be the distance. Find out the work. So work is going to be force vector times the distance vector. We can find out. So force vector is already given, 3, 4, 5. Distance vector, we can find out. That is a PQ length. So if you remember, we're going to subtract 4 minus 2, 6 minus 1, 2 minus 0. So 2, 5, 2. That is a D vector. So we're going to multiply. So work is going to be 3 times 2, 6, 4 times 5. And then 10, you have 36. So this is the work, we just found out by multiply force times distance, because they don't talk about the angle. So you can do this way, or the next question, I'm going to go down. In this time, it's a little bit different. Work is going to be force vector times a D vector, or magnitude of the force, magnitude of the distance times the cosine theta that they're creating, the angle. So a woman exerts a horizontal force of 30 pounds on a craft as she pushes it up a ramp that is 5 foot long and inclined at an angle 20 angle above the horizontal. Find the work. So what happened is there's a 30 pounds, one vector, which is a force, and they how much? 5 foot. This is the distance. And they're creating 20 degrees. So in this time, I want to find out the work, find out the magnitude of the force, which is a 30, it's given. And then distance, magnitude 5, that is a given because we have 2 vector. That is a given. And then you're going to find out cosine theta. So therefore, this is a 30 times 5 cosine 20. So cosine 20, you can use a decimal. That's okay. If you multiply all together, it's going to be 141 foot per pounds. So that's the work that we are looking for. Nothing is special, just same idea, the information between 2 vectors. Last example. Of both sails south with the help of wind blowing in the direction from south to east, creating 30 degrees with magnitude 300 pounds. Find the work done by the wind as the boat moves 150. So we are looking for work. You need a force magnitude because they're mentioning the degree, direction, degree. You're going to use this formula. And cosine theta. Force is what? This is the force. You have east, you have south, and then they're pushing, they're looking for the force. This is the force. They're creating the 36 degree from south to the east. This is a 36 degree. And there's a force. This is the 150 distance. And they're heading to this way, correct? So everything is a given. Force is a 3 pounds times the distance, 150, cosine 36 degree. Just calculate it. Approximately 36,406 foot per pounds. Okay, so as I mentioned, this dot product is using in many physics concepts. So one of the example is work, real life situation, and I also show you more complicated, vector projection. So think about it, vector projection and that formula, and we talk about what they mean algebraically and geometrically in terms of the dot products. So that's a 2.3. So we covered pretty much everything. So definitely, I strongly recommend you read textbook. If you need more information, there are more deep and prove all the information you can find out in our textbook. My lecture is extracting based on the textbook. So you can definitely practice more problems from the textbook. And then there are more embedded video. If you go to 2.3, every quizzes, we have embedded video for each question. And then if you need more help, further help, you can go to discussion board and keep asking and helping each other, okay? So I will see you guys in the next video, and you can finish 2.3, right now. See you guys, everyone. Thank you. See you soon. Bye-bye.